Imagine you're a hospital administrator or a surgical tech. You have a set of high-end surgical tools, maybe orthopedic guides or dental instruments, and they need to be sterilized. Now, sterilization isn't just a quick wipe down. We're talking about an autoclave, superheated steam, high pressure, 270 degrees Fahrenheit, over and over again. Most plastics, they're dead on arrival. They warp, they get brittle, or they literally start to crumble after just a few cycles. Even some high-performance materials start to crack after 50 or 100 trips through the steam. But then, there's PPSU, polyphenylsulfone. This stuff doesn't just survive 10, 20 cycles, it can handle thousands. We're talking about a plastic that can live in a death chamber for years and come out looking brand new. How does a polymer beat out metal in one of the most punishing environments on Earth? To understand that, we have to look at the history and the chemistry behind this super polymer. Before we get into the why and the how, let's talk about why we're even talking about this in the first place. At Vision Miner, we live and breathe high-temperature polymers, PPSU, PEI, PEEK. These aren't just names on a datasheet to us. We've spent the last decade building the machines, the workflows, and the processes to make these industrial survivors 3D printable. Whether you're in the medical field, the aerospace sector, or high-end industrial manufacturing, if you need parts that don't fail when things get hot and chemical, that's what we do. We help you move from prototyping to real-world production. PPSU didn't just appear out of nowhere. It's the heavyweight champion of the sulfone family, which includes polysulfone and polyethersulfone. To find its roots, we have to go back to 1965 at Union Carbide's facility in Bound Brook, New Jersey. Two chemists, Dr. Alfred Farnham and Dr. Robert Johnson, were trying to build a plastic that didn't act like plastic. They synthesized the first high molecular weight polysulfone, which they called UDEL. It was a breakthrough, and industries began to apply it everywhere they could. During this period of mass adoption, a major problem emerged in a very unsexy place: hot water plumbing. In the 1970s and 80s, engineers started using earlier plastics for plumbing fittings and manifold systems. On paper, it looked great, but in the real world, these systems were failing fast. The combination of high-pressure hot water and the chlorine used in municipal water treatments was causing environmental stress cracking. The water essentially was eating the plastic from the inside out, leading to massive property damage and flooded buildings. This crisis was the trial by fire for the sulfone family. Union Carbide realized that to survive in a pressurized, chlorinated 200-degree environment, they needed a molecule that was fundamentally more stable. In 1976, they introduced polyphenylsulfone, eventually known as Radel. By replacing the weaker links in the chain with a massive amount of biphenyl units, they created a material that was virtually immune to the chemical attack of hot, chlorinated water. PPSU didn't just fix the plumbing problem, it became the standard for failure is not an option fluid handling. Eventually, this elite material legacy was carried forward by Solvay, proving PPSU could handle the environments that break everything else. This leads us into how that plumbing durability translated into the operating room. Specifically, let's talk about Radel R5000. In orthopedic surgery, like a total knee replacement, the surgeon doesn't just guess the size of the implant, they use what's called a trial instrument. It's a temporary piece used to verify the fit before the final permanent implant is unpacked. Now, for years, these were heavy stainless steel. They were expensive, they were hard to color code, and they were a nightmare for staff to lug around in heavy trays. When manufacturers switched these trial and instrument handles to PPSU, it was a revolution. Because PPSU is biocompatible and can be pigmented in bright, high-contrast colors, surgeons could instantly grab a size 4 blue or a size 6 red trial. But the magic is in the handle itself. A surgical trial handle made of PPSU can be thrown into a high-pressure steam autoclave, sterilized and cooled down thousands of times, while a material like PEI might start to yellow or show microcracking after only a few hundred cycles. PPSU looks and feels like it just came off the assembly line. It gave hospitals the weight savings of plastics with a service life that finally rivaled the expensive metals they were used to. So how does it do it? PPSU is a polyaromatic ether sulfone. You've got these aromatic rings linked by sulfone and ether groups. Now, rings are like the armor of a polymer. They provide thermal stability. But the secret sauce that separates PPSU from its predecessors is the biphenyl unit. Essentially, the chemists created a chain that is incredibly stiff, but also weirdly flexible at the molecular level. This is the non-trade-off material. In most plastics, if you want it stiff, it becomes brittle, and if you want it tough, it becomes soft. PPSU says no to both. It has the highest impact strength of the entire sulfone family. You can hit a PPSU part with a hammer, and because those molecular chains can absorb the energy without snapping, it just bounces off. We're gonna have to try that. And because of the specific sulfone link, it's chemically bulletproof against hydrolysis, the breakdown by water or steam. It's not just that PPSU can be sterilized, it's that it's virtually unaffected by this process. PPSU isn't just a medical material, it didn't stop at the operating room. It was already proving itself in some of the most demanding environments on the planet, aerospace. Inside an aircraft, materials are constantly exposed to fuel, hydraulic fluids, temperature swings, and non-stop vibration. Traditionally, that metal, aluminum, stainless steel, materials that were strong but heavy, expensive, and difficult to manufacture into complex geometries. PPSU changed that equation. Because of its chemical resistance and its impact strength, PPSU started showing up in aircraft interiors, fluid handling systems, electrical housings, and ducting, places where failure simply wasn't an option. It offered something engineers almost never get: metal-like durability at a fraction of the weight. But there is still one major limitation. You could only get these parts through injection molding. For decades, if you wanted these properties, you had to injection mold the part. That meant $50,000 molds and months of waiting. But 3D printing changed the math. Look at Bell helicopters in the V-22 Osprey. During a technical upgrade, they needed complex branching wiring conduits for testing. Traditionally, these would have been made out of cast aluminum, a process that would take at least 6 weeks of lead time. And instead, they used 3D printed PPSU and printed the entire set of 42 conduits in just 2.5 days. These parts were installed inside the aircraft, exposed to constant vibration, hydraulic fluids, and fuel. Traditional materials would have just dissolved or snapped. PPSU didn't even flinch. We saw the same thing with Parker Hannifin. They 3D printed a prototype for a diesel fuel filter that had to survive being bolted directly onto the engine. It was exposed to high temperature fuel and intense vibration for hours. That's the difference between a model and a functional part. With PPSU, we can finally move from a CAD file to a flight-ready or surgery-ready part in a single day. But here's the catch that held this material back for decades. For years, PPSU was locked behind industrial manufacturing. If you wanted to use it, you needed injection molded parts, long lead times, or a 6-figure industrial 3D printer with a service contract. And on top of that, you were often forced into proprietary ecosystems paying massive markups just to access the material itself. In other words, one of the most capable plastics ever made was out of reach for most engineers, but that's starting to change. A new generation of high-temperature 3D printers like our 22 IDEX is breaking that barrier by bringing PPSU out of just the Fortune 500 labs and into real-world production environments. That shift doesn't just lower cost, it changes how products are designed, tested, and manufactured. Instead of waiting weeks or months, engineers can now go from CAD to functional PPSU parts in a matter of days. And that's where things get really interesting. So where does that leave PPSU today? It's no longer just a niche superplastic. It's quietly embedded in some of the most critical systems we rely on every day. In hospitals, it's still the backbone of sterilizable surgical tools and instrument handles going through thousands of autoclave cycles without failure. In aerospace, it's inside aircraft cabins, fluid systems, and electrical housings handling vibration, chemicals, and extreme environments where weight savings directly impact performance. In industrial manufacturing, it's being used for high-performance fluid handling, filtration systems, and components that would traditionally require metal, but now benefit from the corrosion resistance and lighter weight of a plastic. And now, with high-temperature 3D printing become more and more accessible, PPSU is starting to show up somewhere new. Not just in factories, but in design labs, engineering teams, and production floors that have never had access to it before. For decades, PPSU was a material you designed around because it was hard to access. Now, it's becoming a material you can design with.